All right. So they talk about general forms of a linear function, y equals mx plus b, a quadratic, ax squared plus bx plus c. These are special cases of polynomials. We talked a little bit about this yesterday. Specific types of polynomials are linear and quadratic, but a polynomial can be written in standard form, and that is going to look just like how we have been organizing these things that we've been dividing. An to the times x to the n just means your first coefficient and your highest degree. Let's say that's 5x to the fourth. 5 would be my a sub n, x to the n, that's x to the fourth. So a standard polynomial starts at your highest degree and just goes down from there, which is why this next one says n minus 1 and x to the n minus 1. Whatever my coefficient is, that's my next coefficient, and my next exponent should be lower than my first one. Now, it doesn't mean that you have to have one for each of them like you do when you're dividing. It just means that it's going to go highest to lowest with your degrees, all the way until you get to a constant. That is a polynomial in standard form. So in standard form, you go from your highest exponent to your lowest exponent for a polynomial. It says n is a non-negative integer and the coefficients are real numbers, all right? So we're not going to have negative integers here. In other functions we can, but if it's considered a polynomial function, then our integers will all be positive. Our exponents will all be positive, and our coefficients are real numbers, all right? So we're not talking about like imaginary numbers like we've used in the past when we worked with imaginary numbers. They're all real numbers. So that is the definition. In the last section, we learned that if we get a remainder of 0, we know that it is a factor, all right? Just like anything else, if you divide by a number and your remainder is 0, that number is considered a factor of the number that was divided, okay? Something else the remainder tells us. The remainder also tells us what would happen if we were to plug the number in, all right? So let's look at this example. It says, given the polynomial function, and they give us this big old polynomial, the value of p of 2, that just means plug it in. So remember, if you have f of a number or the function with the parentheses, it doesn't mean multiply. It means plug that number into the function. All right, so if I take 2 and I plug it into this, so 3 times 2 cubed minus 4 times 2 squared plus 2 times 2 minus 8. Plug it in, I get 4, all right? So if I plug a 2 in, my answer is 4. Let's do synthetic division. So we took our coefficients, 3, -4, 2, and -8. And we are going to do synthetic division with this. Remember, it's the opposite, right? So x minus 2, we're going to do synthetic division with a 2. 3, add down, multiply up. Add down, multiply up. Add down, multiply up. Look at our remainder. What do you notice about your remainder?
It's the same as
Hopefully, you notice that, all right? That will always be the case. All right, your remainder tells you a couple of things. A 0 tells you you have a factor, but any remainder tells you what would happen if you plugged that number in. Sometimes it is faster to do synthetic division than to plug it in and do order of operations. All right, and they will give you the same answer. All right, so it's called synthetic substitution, and it is the remainder theorem. If a polynomial, p of x, is divided by a binomial, the remainder is p of a. All those words are saying the remainder represents what would happen if you plugged in the number into the function. If you plug the number into the function. So let's look at this example. Find the remainder when this polynomial is divided by x minus 1. All right, x minus 1. So we're going to do synthetic division here because remember, if it's just x minus or plus a number, synthetic is usually faster. My coefficient here is 1. My cubed coefficient is -6. My squared is -1. This is 2, and then I have 7. And remember, I'm going to say what happens when this equals 0. So I'm actually going to use a positive 1 out here. Positive 1. All right? And then I'm going to do the synthetic. I'm going to add down. I'm going to multiply up. All right, so all I'm doing is finding the remainder. There is my remainder, all right? Now I'm going to plug in a 1. So we're actually going to check this theorem. We're going to plug a 1 in. 1 to the 4th minus 6, 1 cubed minus 1 squared plus 2 times 1 plus 7. I get 1 minus 6 minus 1 plus 2 plus 7. All right. 1 minus 6, that's negative 5. Negative 6, right? Negative 4 plus 7 equals 3. All right. So using synthetic division and taking your remainder is another way to figure out what would happen if you plugged the number in. That is what the remainder theorems tell you. All right. So the remainder theorem tells you that the remainder is going to be what happens when you plug the number in. And then the factor theorem, which is what we already talked about. The factor theorem tells you if that remainder is 0, yes, if you plug the number in, you would still get 0. But it also tells you that it is a factor. And so there are a couple ways they can ask the same question. The first thing they can say is it a factor, right? Or they could say, find the factor. Or they could say, find the 0. All of these are asking the same question, and you can do different methods to find it. Synthetic division is one of the ways you can do it. So if you look at this next example, determine whether x plus 2 is a factor. One of the ways you can determine that is divide. If you get a remainder of 0, your answer will be yes. And so we're going to use synthetic division here to answer the question. Is this a factor? Well, let's do the synthetic division and find out. We're going to put our coefficients there. For x plus 2, what am I going to put out here?
-2.
A negative 2. And then I'm just going to go down. So 1, negative 2, this is 0. Remainder of 0, yes, it is a factor. All right? And so one of the ways you can figure out if it's a factor is by simply figuring out, do you have a remainder of 0? So we talked about a little bit what a zero is. A zero is where it crosses the x-axis. All right. Anytime you see this piece of it, this long piece of it, they're just saying given a polynomial. All right. Given some polynomial function. So don't let all the little numbers and letters scare you. Let's say they give you a polynomial function. It has integral coefficients, so it has rational zeros. In simplest form, it will always be a factor of your first and last term. So if you are looking for a zero, the first place to start is to look at your first and last term. Remember, a zero is also called our x-intercept, where it crosses the x-axis. And so if we're trying to figure out where this could cross the x-axis, we can start by looking at the last term and the first term. The last term is our constant. We have a -6. It really doesn't matter if it's positive, negative, because you're going to end up using both factors anyway. All right? My factors of 6 are going to be 2 and 3. All right? Or it could be positive or negative 2 or 3. All right? So I could say positive or negative 2 or 3. Then I'm going to look at my first factor, my first element here, my first term. My coefficient here is a 1. The factors of 1, obviously, we only have positive 1 or negative 1. That's my only options for 1. And what they're saying is every single zero of this polynomial will fall within the factors of my last number. So factors of 6 over factors of my leading coefficient. Every one of them. And so I'm going to say my possible zeros. That's what they're asking. What are the possible zeros? They are going to be positive and negative 2 over 1, positive or negative 3 over 1. All right. There's one more factor that is always going to be an option. All right. It's going to be 1, right? 1 and the number. So 1 times 6 will also give me 6. All right, so I have to also consider a positive and negative 1 and a positive and negative 6. Those will always be factors that you're going to use. So that our remainder should be 0. All right, because if I plugged it in, I get a 0, which is what that means. So if I do this and do my number here, that's what I should get. If I don't, and they told me it was a 0, I did something wrong. So I automatically know that 2 is a 0, and I automatically know that x minus 2 is a factor. All right? So then what does the rest of this look like? Well, I started with x cubed, so it's going to give me x squared minus 1x plus 3. How would I find my other factors here? Well, that is it. This is not factorable. So all I can do is say, well, that's going to look like this. If that were like a -2, a positive 4 or something, I could probably factor it, or a negative 4, I could factor it. But there are no factors of 3 that subtract, that 2 negatives add up to give you a 1, because the only factors of 3 are 1 and 3. So this is as small as it's going to get. These are my factors of that equation. So for this one, it says list all the possible. We're actually going to do this together. So I'm going to start with my 3. What are all of my factors of 3? Well, that's easy. 1 and 3, positive, negative 1, positive, negative 3. That's going to be my numerators. All right. My first number is a 2. What are all my factors of 2? Well, that's also easy. Positive and negative 1, positive and negative 2. Here's the thing. Every single one of those has to be put over every single one of those. All right. So I'm going to start with my 1. It can be positive and negative 1 over 1, which just reduces to positive and negative 1, right? It could be positive and negative 3 over 1, which just reduces to positive or negative 3. That's possible. Then I could be positive and negative 1 over positive or negative 2. Another way to write that is positive or negative 1/2. Or it could be positive or negative 3 over positive or negative 2. Positive or negative 3/2. Every single one of your factors of your last one over every single one of your factors of your first one. Those are your possible zeros for that. Those are your possible zeros. All right? So when you have an example like this, you have a polynomial, 2x cubed plus 3x squared minus 1, and they want us to factor. We cannot go back to our standard factoring that we've done in the past because this is not a quadratic. This is actually a degree of 3. A quadratic would be a degree of 2. So if this were 2x squared plus 3x minus 1, we could potentially say, well, can I factor it using my standard method of multiplying across? Or can I find my zeros by doing quadratic formulas, something like that? But this is not a quadratic. All right, this has a degree of 3. A quadratic has a degree of 2. So I can't go to my standard factoring. So what I can do is I can say, what are my possible factors? Well, my possible zeros are going to come from this last number and this first number. So my factors of 1, it's just 1, right? My factors of 2 are 1 and 2. So I can put 1 over 1, that's positive or negative 1. And I can put 1 over 2, positive and negative 1/2. So I know that my zeros are going to come from those possibilities, all right? And so typically when I give you these, I am going to give you one of your zeros so that you can get to a quadratic that you can then factor. And so I am going to go ahead and tell you we are going to start with negative 1. So normally I will say given one factor of like x plus 1. I'm going to say given that that is a factor, do the rest of it. And so what we're going to do is we're going to use synthetic division to do this. So if they give you a factor, you're going to start with synthetic division. On the outside here, what am I going to put? Yeah, I'm going to put negative 1 because I have x plus 1, set it equal to 0. So out here, I'm going to put negative 1. And on the inside of my synthetic, I'm going to use my coefficients. My first coefficient is 2. My coefficient of x squared is 3. I do not have an x, so I need to put a 0 there. And then my constant is negative 1. If they told me that's a factor, what should my remainder be? 0. So if they told me it's a factor, I should do this and get a remainder of 0. If I don't, I did something wrong because they told me this is a factor, all right? So I'm going to add down. I get 2, multiply up, negative 2, add down, get 1, multiply up, get negative 1, add down, multiply up, 0. That is what I'm looking for if they told me it was a factor. So they want me to factor this. The first thing I'm going to write down is the one that they gave me. That's one of my factors, all right? And then I am going to rewrite this with my x's. So I started with an x cubed, so now this is going to be 2x squared plus 1x minus 1. This is a quadratic. If it can be factored, I can use my factoring techniques to do it, all right? So for this one, if you don't remember, you can multiply across, right? 2 times negative 1 is negative 2. Factors of negative 2 that add up to 1, well, that's going to be a positive 2 and a negative 1, right? And then I'm going to rewrite this, 2x squared. Leave that alone. I'm going to rewrite that with these factors that I just came up with. So I'm going to say plus 2x minus 1x minus 1. All right? How do I factor 4 terms? If it's possible, I factor by grouping, right? So I'm going to group these two, group the last two. If I group behind a negative, change the sign. What can come out of the first group? 2x, right? And I'm left with x plus 1. If nothing can come out, I'm just going to put a 1 there. And I'm left with x plus 1. All right? And then my final thing is my factors are x plus 1 and 2x minus 1. Those are my remaining factors of this. So if I go back up here, I'm going to write those down. Those are my 2 other factors. All right? So if it says factor completely and they give me a factor, I can divide using that factor. And then if it then drops you to an x squared, then you can look at your other ways of factoring and see if it's factorable. If I were to multiply all 3 of these out, I should get that. It is a way to check it. You can multiply it and check it and see if you got the right factors. All right? So when we did our bell work, we actually multiplied these. All right, so on your bell work, you had 2a and b, which was actually a plus b on your bell work. And you were multiplying that by a squared minus ab plus b squared. And when you multiplied it out, you got a squared plus b squared. All right. These are special case factoring. So if you'll remember, I like to relate it to difference of two squareds. If you remember, if you get something like x squared minus 9, and you need to factor that, that's a special case. Two perfect squares that are subtracted will always factor to the plus and the minus of the roots. That's a special case. That's what these are, okay? These are special cases. It's actually two of them. So they just listed it out together, but there's two of them. The first one is if you have perfect cubes that are added, all right? So you have perfect cubes that are added and they want you to factor it. It's always gonna factor to the cubed root, and we're gonna do some of these. So whatever the root is, you're going to add that. And then the next one is going to be the first one squared minus what happens when you multiply them plus the last one squared. That's if they're added. If they are subtracted, let's say you have two perfect cubes that are being subtracted, then it's going to be those two subtracted, and then it's going to be all pluses for the second group. All right, so they just wrote it with the plus and minus together. But if it's adding, it's going to be adding here and subtracting here. If it's subtracting here, it's going to be subtracting adding. So that it's actually two different ones. They just wrote them together, okay? They just wrote them together. So if you have two perfect squares, let's say x cubed, or two perfect cubes, x cubed plus 27. 27 is a perfect cube, all right? Then you would take the cubed root and do it. So we're going to do a couple of those so you can see it, all right? But those are the special cases. They're just written out as one. So look at example 5 in your book. All right. So the first thing you notice is that we have a perfect cubed, x cubed, and we have a perfect cubed, 64, and they are subtracted. So we are going to use the subtraction one. The first thing we need to do is say, what is the cubed root? Well, the cubed root of x cubed is just x. The cubed root of 64 is 4. So those are the A's and B's that we're going to use to plug that in. All right. So this is the same thing as saying x cubed minus 4 cubed. All right. X cubed minus 4 cubed. That's x cubed minus 64. All right. And then we are going to just factor it according to this. I'm going to say if this is my A and this is my B, I'm going to start off with x minus 4. That's in the first group. And in the second group, it's the x squared plus the x times the 4 plus the 4 squared. That's like my a squared plus ab plus b squared, all right? So this is my a, this is my b, and then I just did a minus b, a squared plus a times b, plus b squared, all right? I do want to make that second group a little more simple than that, right? So I'm going to rewrite that second group. I'm going to leave this x minus 4 alone. The x squared is as simple as can be, but I would write x times 4 like this, 4x, right? And I would write 4 squared like this, 16. And that would be how I would factor that group. If I were to multiply those two, I would get x cubed minus 64. All right, and so my answer here is going to be the factoring looks like this: x minus 4, x squared plus 4x plus 16. All right, if I were to multiply those, I should get what I started with. That's how I would check it, just like any factoring. All right, let's look at the next one. The first thing I'm going to check is, are they perfect cubes? Well, yes, 8 has a perfect cubed root of 2. And of course, c cubed, the root there is just c. So I can rewrite 8c cubed like 2c if I were to cube it. That would be my a. And then plus, does 27 have a perfect cubed root? Well, yeah, that's going to be 3. And then d to the 6th, all right? I'm looking to see, is that divisible by 3? Is 6 divisible by 3? Well, yes. 6 divided by 3 is 2. So that's the same thing as saying if I were to take d squared and cube it, all right? So if I were to say 2c and cube it, I would get 8c cubed. If I were to do 3d squared and cube it, I would get 3 cubed, 27. And then remember, those are multiplied, d to the 6th. So this is my a, and this is my b in this situation, all right? And then I'm just going to write out my factoring. So I am going to say, well, this is a plus, so I'm going to use the plus one. I'm going to say a plus my b, and I'm going to multiply that by my a squared minus my a times my b, and then plus my b squared. All right, so all I did was fill in that formula for the factoring. And then, of course, I do want to simplify this. So this is as simple as it gets. So that's going to stay 2c plus 3d. I want to simplify this. What happens if I square that? Well, 2 squared, that's going to be 4, and of course, c squared. Minus, I want to simplify this. 2 times 3, well, that's 6. And then I just have c and d squared. So that's that. And then I want to simplify this. That's a squared. All right, so when I simplify that, 3 squared is going to give me a 9. D squared squared is going to give me a d to the 4th. And so that is my answer for that factoring. So you really need to memorize this factoring here. You need to memorize if it's a cubed plus or minus, what's the factoring there? All right, so let's try. So the other larger factoring, so we've done factoring with squareds, but now we're looking at factoring with larger. So one way is synthetic division. Given a factor, you can divide it out and then find your other factors. Or a perfect type of cubed plus or minus. That's a special case factoring. You can also have something that looks very much like a quadrilateral, but you'll notice your degree is larger, okay? So let's say you have something like this. It's 3 terms, and you notice that this is larger than your standard square if it were 3 terms, all right? All you have to do is say, okay, if this is a 4th, make sure this middle term is half, all right, of that. So this is 4, this is a 2. You can pretend you factored this just like anything else. So if I were to have something like x squared minus 5x plus 4, I would say, well, factors of 4 that add up to 5. That's 1 and 4. And my factoring would look like this, x minus 4, x minus 1, right? And if you were to FOIL that, you would get x squared minus 5x plus 4. We're going to do the same thing over here. Factors of 4 that add up to 5, but instead of x's here, we are going to use x squared. All right, so we're going to use what would multiply to give us x to the 4th. Well, that would be x squared minus 4, x squared minus 1, all right? That's going to be the same thing. If I were to FOIL it, x squared times x squared gives me x to the 4th. x squared times negative 1, negative 1x squared, minus 4x squared. Well, that gives me negative 5x squared. And then negative 4 times negative 1 gives me positive 4, all right? So you can see how this is the exact same factoring as this. The only thing you have to look out for is, do I create a special case when I have an x squared? Because we just talked about one of our special cases. One of our special cases is a squared minus b squared. Two perfect squares can factor to a plus b, a minus b. So I have to look for that when I have a higher exponent, because when I factor, I'm still going to have an exponent that could potentially continue to factor. And in this case, it does. X squared minus 4 is a perfect square, and they are subtracted. So I can keep going. I can say, well, that can be written as x plus 2, x minus 2. Well, x squared and 1 are also perfect squares. So I can continue factoring and make that an x plus 1 and an x minus 1. All right? And so you do the initial piece exactly the same as you would if it were a squared and a to the 1 power. But then you have to check it and say, can I continue to factor? Is it a special case from there that I can factor more? And in this case, it was. And so this factoring would actually look like that. Very last example here. They've given us a 4-term. We've done a 4-term and it did not factor by grouping, but anytime I am given a 4-term polynomial, the first thing I check is, could you factor by grouping? If I were to group it and factor something out, would I get the exact group? And if that's the case, I can factor by grouping. I don't have to do synthetic division if it will factor by grouping, all right? And so anytime I have a 4-term, the first thing I say is, could I factor by grouping? If I can't, then I'm going to say, well, I'm going to try 1 or negative 1 and see if I can do synthetic division, all right? And get it down smaller. But if you're given one that can factor by grouping, that's one of the ways that we've learned to factor larger polynomials. We can factor them using grouping. And this is one that you can do it with. I can group the first 2. I can group the last 2 and change the sign because I grouped behind a negative. Then I'm going to look at the first group. In common, they have an x squared. And when I take it out, I get x minus 5. The second group, well, those have a 9 in common. When I take that out, I get an x minus 5. All right? And so then I can factor this by grouping because these are the same. If those are not the same, you will not be able to factor by grouping. You'll have to do like your synthetic division or something. But if they are, you can factor by grouping. I have x minus 5 in common, and what's left over is x squared minus 9. Am I done factoring? So if you look at this, this is as small as it can get, but this guy is just what we had up here. We have 2 perfect squares that are being subtracted. So I can keep going with this one. I am not done. The x minus 5 is as small as it can get. But for this next one, I can break it down into x plus my square root of 3 and x minus that square root of 3. And that is as small as I can factor that particular one.